Welcome back to the next video. Everybody, we're going to continue looking at proposition 4. We're going to go back to the symmetric square L function to do so. Please watch the previous few videos, especially for notational reasons if you haven't already or if it's been a while. So we're going to take a finite set of prime sigma in sigma sub rho bar, as we've been doing for a while now, and we're going to let F be a new form in n sub sigma with coefficients in O, our discrete valuation ring. And what we want to do this video is relate bracket xy sub h, which is a gadget we came up with last video from the previous corollary, to L sim squared f evaluated at 2 using a result of theta. So for that, you can see congruences of cusp forms and special values of their zeta functions, section 5, if you'd like to see more details than what I give you today. We'll begin by recalling that there's a homomorphism from T sub O to T sub frac M, where M is the maximal ideal here in T associated to F. That's isomorphic to T sub sigma by a crucial result from this chapter. And then there's the map pi from T sub sigma to O in our surjective triangle of commuting O algebra homomorphisms. And so if you actually just unwind definitions, this composition from T sub O to O is nothing but the map that sends the Hecke operator T sub n to A sub n of G, where G is the special eigenform in S2 gamma 0 n with coefficients in K associated to the F that we started with. We built this G several videos ago. Okay, so we'll let curly P denote the kernel of this composition. This is the pre-image in T sub O of what we called WP before. In T sub sigma, after noting that P localized at frac M corresponds to WP under the isomorphism between T sub frac M and T sub sigma. Again, there's a lot of notation in this video. All of it has been described and defined for you in this chapter. Okay. So we're going to let K sub 0 be a number field containing the Fourier coefficients of that G, and we'll let O sub 0 be O intersect K sub 0. And then we'll let P sub 0 be P intersect T sub O sub 0. And we'll choose a basis xy for LH bracket WP in the image of the composition that I just described above. Okay. Again, this LH module, this was described last video. So which composition am I talking about? The composition is H1XO0 bracket P0, which lives inside H1XO bracket P. Now, that's isomorphic by proposition T sub M with H1XO localized at M bracket P, which is just by definition LH bracket WP. And so the composition I'm talking about here, whose image I want you to choose a basis XY for, is the image of this guy here. Okay, so let's keep going. We'll let P sub C denote the kernel of the homomorphism theta sub G from T sub C to C associated to G. Okay, so that's just kind of tensoring up to C and realizing that these eigenforms are associated to maps out of the corresponding Hecke algebra. You can see chapter 3 for more information about that if you forgot all that. If omega sub G denotes the usual holomorphic differential on the modular curve X associated to G, that is the holomorphic differential sum of the coefficients A sub n of G times Q to the n minus 1 dq. Then the two-dimensional complex vector space H1x O naught bracket P0 tensored up to C over O naught, which is H1x C bracket P sub C, actually has canonical basis omega sub G omega bar sub G to the C, where C indicates complex conjugation. So this is well-known kind of information that you could derive back from information as early as chapter 3 in this playlist. Okay, and so what we're going to do is we're going to let A be the 2x2 invertible matrix with complex entries that satisfies the following property. It's kind of the change of basis matrix. It's the matrix such that when you take x, y, and multiply by A, you get this canonical basis, omega sub G, omega bar sub G to the C. So it's kind of this transitional matrix from one basis to another. Okay, and so here's the main result of the video. So theorem, we'll call it theorem sim squared. We have the following relationship between bracket sub H and L sim squared F evaluated at 2. It's the following. Bracket xy sub H is nothing but I pi times the determinant of A inverse times n sub F, which is the level of F, times L of sim squared F comma 2 times the product over primes P dividing the quotient n over n sub f, the n given to us and n the level of f, of the C sub P of f's. And the C sub P's were defined this chapter as well. Okay. Oh, it looks like I actually give you the definitions again here. The definitions are as follows. C sub P of f is P to the delta sub P, L sub P of sim squared f2 inverse if P isn't L. And it's alpha sub L of f minus beta sub L of f times 1 minus alpha sub L to the negative second of f if P is L. And all of the missing definitions here can be found in video 11.9, specifically what this delta sub P is, what these local L factors are, and these guys are your roots of your characteristic polynomial. So all of this was defined before. Okay, so very notation heavy video. But the point really is this. We have this relationship and this is what we need. Okay, so let's look at the proof of this. First, bracket xy sub h times the determinant of A is the integral over the modular curve x of omega sub g wedge omega bar wg to the c, where I will describe all missing pieces in a second, but this ends up just being 8 pi squared I times bracket gwg to the c. What are these last brackets here? They are the Peterson inner product from chapter 3. Okay. W is our involution that we've been talking about this chapter. And we are using the fact to make this actually calculate out the right way, that wg to the c is actually w of g all to the c on gamma 0 of n. Okay, so we have this equality just by calculating things out straight. Then a result from Shimura, the special values of the zeta function associated with cusp forms in section 2.5. And you can also see that same congruences of cusp forms paper I talked about earlier, 5.13. It lets me actually calculate this. This is just a Peterson inner product. I know how to calculate this. It ends up being 48 pi inverse times the index of gamma 0 n and SL2z times the residue at s equals 2 of what we'll call d of gwg comma s, where in general, d of GHS is defined to be the following gadget. It's the sum of the a sub n of g's times the a sub n of h's, so g and h are cusp forms here, times n to the negative s. So it's kind of a little Dirichlet series over 2 different cusp forms. Okay. So if G and H are normalized eigenforms, you can actually just compute the Euler product expansion of this guy. And here's what you get here, the factors. They're kind of big, so get ready. So the factors are 1 minus alpha sub p of G, beta sub p of G, alpha sub p of H, beta sub p of H, p to the negative 2s, times 1 minus alpha sub p of G, alpha sub p of H, p to the negative s inverse, times 1 minus alpha sub p of G, beta sub p of H, p to the negative s inverse, times 1 minus beta sub p of G, alpha sub p of H, p to the negative s inverse, times 1 minus beta sub p of G, beta sub p of H, p to the negative s inverse. So it's like all possible combinations of symmetries between G and H and their corresponding p coefficients, not p coefficients rather, but their roots of their characteristic polynomials at Frobenius of p. Like it's every single possible combination is what you get. There's a lot of symmetry here. Okay. If you then go back and look at how G was created from F, you can quickly check that if L is a prime not in sigma, if the given prime L is not in sigma, then d of G WGS is nothing but plus or minus d sub sigma FFS times the product of all primes P dividing n over nf of P inverse, where what is this d sub sigma here? The subscript sigma indicates we've removed primes in sigma, where we've removed the factors in sigma from the Euler product. That's all. Okay, so this is a kind of an unwinding definitions check again. What happens if L is in sigma? You get the same thing, except for you also have to multiply by one of the 2 following factors, either 1 minus L to the negative s inverse if L does divide the level of F, or 1 minus L to the 1 minus s inverse times 1 minus alpha sub L squared of F, L to the negative s inverse times beta sub L of F minus alpha sub L to the 2 minus s of F if L does not divide n sub F. Okay, so we have a concrete relationship between this guy and this guy in all cases, essentially. Okay. Then you compute using Euler product expansions. Again, this is more just like unwinding definitions and comparing things that you already know how to calculate. You can actually calculate this guy d sub sigma of FFS up here because you have an explicit definition of it. And you find that it's zeta sub n of s minus 1 times L sub sigma sim squared f evaluated at s over zeta sub n of 2s minus 2, where zeta sub n is the Riemann zeta function with the Euler factors corresponding to primes dividing n removed. And L sub sigma is my L function with primes, with factors at primes in sigma removed again, as usual. So we have this relationship here. And so this allows you then to use the formula we discovered at the beginning of the proof to calculate that missing residue we are after. So the residue at s equals 2 of d of GWGS turns out to be nothing but plus or minus 6 over pi squared times n times L sub sigma of sim squared f comma 2 times the product over primes p, dividing n over nf of those primes p, divided by that index of gamma sub 0 of n in SL2 of z. So this is just combining everything we've discovered so far. That's all it is. Basically, this res guy here is something we were missing in the formula to finish the proof, and now we get a formula for it thanks to things we already know. Okay, and then there might be an extra factor here of 1 minus L to the negative second to the minus first, or that beta sub L of f minus alpha sub L of f times 1 minus beta sub L negative second f inverse times 1 minus L to the negative first inverse if L is in sigma. Okay, so it depends basically on whether or not L is in sigma, what that extra factor on the end here is. Okay, but if you actually then just go take all of this and you plug it in for res sub s equals 2 of d of GWGS, you find that you just end up with the formula we're trying to prove. Okay, and so that's an exercise that I'll let you do. What we really need from this is the following corollary that we will use later. It says the following: we have L to the m times n sub f times L sub sigma of sim squared of f evaluated at 2 divided by I pi det A is in that O naught from earlier. And as a matter of fact, it is nothing but a generator of the congruence module eta sub sigma. The only thing I have to do here is tell you what this m is. M is 0 if L isn't in sigma. It's 2 if L is in sigma and L divides n sub f, and it's 3 otherwise. Okay, and so what we have found is a single generator in terms of that matrix A that generates the congruence module whose size we're trying to get a handle on, eta sub sigma, and that's going to be incredibly useful for us. Okay. Now, it seems like we did a lot of work for very little, but I'll note here that without theorem TH from the previous videos and its corollary, which we haven't used yet, by the way, we would have actually only been able to show that eta sub sigma is contained in the ideal generated by this guy rather than it's equal to that ideal, and that wouldn't be good enough. Okay, so there's a lot of details in this video for you to check, but they're all kind of just like sit down, write down definitions, calculate and compute things. Okay, I will leave it to you to check as a pretty easy exercise that this corollary does indeed follow immediately from the main result of this video, but I don't want to get bogged down in super technical details here. And so I'll see you all next video where we'll head towards concluding the proof of proposition 4 finally. And so I'll see you then. Happy holidays. Thanks for watching.